Insertion in a binary search tree follows the property that the left child is smaller than the parent node and the right child is larger than the parent node. When inserting a new node, we start at the root node and recursively find the correct position for the new node, ensuring that the binary search property is maintained. Let us see the steps for the insertion. The first step, we start at the root. If the tree is empty, the new node becomes the root. Second step, compare the values with the current node. If the new value is less than the current node, move to the left subtree. If the new value is greater than the current node's value, move to the right subtree. Third step, repeat the comparison process until the current position is found. That is when you reach a null position in the tree. Step 4, insert the new node at the null position. Let's understand this with an example. Suppose we want to insert the values 50, 30, 70, 20, 40, 60 and 80 into a binary search tree. Insert 50. This becomes the root node of the binary search tree. Next, insert 30. Since 30 is less than 50, so 30 becomes the left child of 50. Now insert 70. Since 70 is greater than 50, so 70 becomes the right child of 50. Insert 20. Since 20 is less than 50 and 20 is less than 30, so 20 becomes the left child of 30. Insert 40. Since 40 is less than 50 and 40 is greater than 30, so 40 becomes the right child of 30. Insert 60. Since 60 is greater than 50 and 60 is less than 70, so 60 becomes the left child of 70. Insert 80. Since 80 is greater than 50 and also greater than 70, so 80 becomes the right child of 70. This is the final tree structure. Insertion algorithm. First check if the root tree is null. If yes, create a new node with the given value and return it as a root. If the value is less than the current node's value, recursively call the function to insert the value in the left subtree. If the value is greater than the current node's value, recursively call the function to insert the value in the right subtree. Return the root after inserting the new node. Time complexity of the insertion in binary search tree is: average case is big O of log n for balanced trees and worst case is big O of n for the skewed trees where the tree resembles a linked list. Deletion in binary search tree involves removing a node while ensuring that the property of the binary search tree left is less than root and root is less than right. There are three possible cases to consider when deleting a node. Let us see the cases for deletion. Case 1. Deleting a leaf node, that is node with no children. Here you can just simply remove the node. For example, we remove the 20 from this tree. The tree becomes like this. Case 2. Deleting a node with one child. Here we replace the node with its child, either left or right. Say for example, if we delete 30, it has one right child, that is 40. So the tree becomes like this. Case 3. Deleting a node with two children. Find either the in-order processor, the largest value in the left subtree, or in-order successor, is the smallest value in the right subtree. Replace the node with the in-order predecessor or successor and remove the predecessor or successor node from its original position. For example, in this tree, if we delete 50, in-order successor of 50 is 60, that is smallest node in the right subtree. Replace 50 with 60 and then delete 60 from its original position. The tree becomes like this. Deletion algorithm. First check if the tree is empty, that is root is null. The function returns null. This handles the edge case where tree is empty. The function first searches for the node that needs to be deleted. If the value is less than the current node value, it moves to the left subtree. If the value is greater than the root value, it moves to the right subtree. This process continues recursively until the node with the value to be deleted is found. Once the node to be deleted is found, there are three possible cases. The first case is no child, that is leaf node. If the node is leaf, it can be deleted directly by returning null, effectively removing it from the tree. Case 2, that is with one child. If the node to be deleted has only one child, if it has the right child but no left child, the function returns the right child, which takes the place of the node. If it has left child but no right child, the function returns the left child, which replaces the node. Case 3 with two children. If the node to be deleted has two children, the in-order successor, that is smallest value in the right subtree, is found using the find min. The current node's value is replaced with the value of the in-order successor. The in-order successor node is then deleted by recursively calling the delete node on the right subtree with the successor's value. Finally, the function returns the updated root after deletion, which allows the changes to propagate upwards in recursive calls. This method ensures the properties of the binary search tree are maintained after deletion. Let us see the time complexity of deletion. Best case with the balanced tree is big O of log n. Worst case with the unbalanced tree is big O of n. This algorithm maintains the structure of the binary search tree and ensures efficient deletion while keeping the tree's ordering property intact. Searching in binary search tree. A binary search tree allows for efficient searching of values based on property, where each node follows a specific order. Left subtree contains nodes with the value less than the parent node, while right subtree contains nodes with the values greater than the parent node. Let us see the steps for searching a binary search tree. Now we will search for a value, say for example 60 in the following binary search tree. First start at the root. Root is 50, target value is 60. Since 60 is greater than 50, move to the right subtree. As we move to the right child, the current node is 70. Since 60 is less than 70, move to the left subtree. After moving to the left child, the current node is 60. The value matches. So 60 is found in the tree. And the time complexity of the searching is, in the best case of the balanced tree, is big O of log n, and worst case of unbalanced tree is big O of n. The efficiency of searching in a binary search tree depends on its balance. In a balanced binary search tree, search operations are very efficient. Algorithm for searching in the binary search tree. First step is to start at the root node of the tree. If the tree is empty, the search ends. The element is not found. If the target value is equal to the current node's value, the search is successful and the node is found. If the target value is less than the current node's value, move to the left subtree. If the target value is greater than the current node's value, move to the right subtree. Repeat the process until the node is found or a leaf node is reached, that is, if the element is not found.